Okay, welcome to the extension to Saturday. Yay! For our first panel, we have our resident scientific expert, Dr. Bob.
Oh no! Screen optimization is complete. Woohoo! Did that go away?
We'll see.
Okay, right. In the meantime, you may not be able to see. Right.
There you go.
Right, okay, so
Right.
what I'm going to do is, you can see my funny example there, stolen from the go-to. In science fiction, often, you know, the Enterprise or whatever is trawling about through space and they keep discovering Earth-like planets. Okay? This talk is going to point out the fact that Earth was not a very Earth-like planet through most of its geological history. Okay? So when you say Earth-like, you've got to be a bit careful. I'm going to go from the present back gradually further and further through the past because it's quite useful for science fiction. You can find inspiration for worlds you want to create for your novel or your TV series or your role-playing game. I will be doing some risk assessments for time travellers, handy health and safety tips. And if you're into what's known as cli-fi, science fiction about climate change, we'll be having some stuff to actually some sodding science into your cli-fi. And quite frankly, a lot of people that talk about climate change in the media and on the news and in politics also need freaking science. Yeah. Grant available in the bar at no added extra cost. Okay. So the first thing is, Earth has two default climate settings that it switches backwards and forwards between. They're known as ice house and greenhouse. So I have some typical pictures of an ice house climate and a greenhouse climate from prehistoric animal books. Anyone want who thinks our current climate is greenhouse and who thinks it is ice house? Votes for greenhouse?
I'll vote for intermediate.
No, it's either one or the other.
Interglacial.
It's an interglacial, but it's either one or the other. No votes for that. Who votes for ice house? Way, you're all well-educated people. If we have ice caps at the poles, it's an ice house climate. Even in an interglacial, okay? Even if a teeny tiny pathetic ice caps at the poles. So, despite heat waves, if you've got permanent ice or at the poles, you're in an ice house climate. And this geological column here shows you all the bits that are in different colours. Blue are when we had an ice house climate through time, back it's 850 million years ago up to the present. All the bits that are in pink are when we had a greenhouse climate. Dark blue means more severe ice house flow and ice ages. The red bits means more severe greenhouse. I will be talking about that in a bit. But as you can see, backwards and forwards, backwards and forwards, backwards and forwards. Therefore, a lot of science fiction assumes, because Earth-like is now, all planets will have ice caps. This is the official map from June. It's the northern hemisphere of June, and if you zoom in on the pole, there's the polar sink, there's the North Pole, and there's an ice cap. Even June has an ice cap. Now that might be because everyone, lots of science fiction assumes ice caps are normal, or it might be because Frank Herbert was actually into ecology quite a lot and had figured out you can have a planet with no freaking water but still have a bit of ice at the poles. See Mars. And the official June encyclopedia, which was sanctioned by Herbert but not written by him, there's a little entry about how the Harkonnens did this. Lots of people are mining the ice at the pole to supply water, for elsewhere. Right. So mentioned, you know, we have the polar ice caps as one thing of the ice house, but there's a whole bunch of differences between ice house worlds and greenhouse worlds. So, because all the water is locked up as ice, it can't fall as rain, and it can't be in the sea, and so on. So, sea level is reduced. Also, there's in greenhouse, when it's warm, there's also what's called thermal expansion. The same amount of water, but it expands. There's a lot less rainfall, and including snowfall in an ice age, in an ice house. Rains a ton. Higher wind speeds in an ice house climate, because the difference, that's the global average, because the difference between the temperature at the poles and the equator is more in an ice house climate, and that drives things like jet stream and so on. So greenhouse, you get the unbelievable hurricanes like we've had in Jamaica all the freaking time, but despite those high wind speeds in that band, globally there's more wind in an ice house climate. So it will be windier in Aberdeen and Norway than it is now, but maybe, you know, less windy at the equator. Less water, the deserts get bigger in ice house, and they shrink in a greenhouse. So all the climate fiction, where they portray the planet as a desert, it should rain all the time. You know, it's going to be more like Manchester than it is like grasslands love it when it's dry. Forests hate it. So when it gets warmer, you get more bigger forests. I'll do that a bit. I will tell you more about that in a bit. And chemical weathering. Any chemical reaction, if they put the temperature up, it increases. So it's like if you raise the temperature by 10 degrees, the speed of the chemical reaction doubles. So if you even if you're putting up the temperature a bit, chemical reactions happen faster, which means the organic material in the soils breaks down faster, simply by chemical reaction without actually bacteria eating it. So soils become less fertile in warmer climates. So a lot of tropical soils are lateritic and have next to no organic material in them, whereas we're used to deep, you know, all the lovely humus kind of, you know, Lenny Henry doing David Bellamy. This thing out at the bottom is how much ice cover there's been in Antarctica over recent geological time. For some reason, black is the ice and white is the not ice in this particular scientific paper. Who knew?
That's really bad colour blindness.
Yes, yeah, it's terrible trouble on zebra crossings. Right, okay, so yeah, we have the day after tomorrow, which is not a good guide to how it is. The last 34 million years, we've had a succession of full-on ice ages and then interglacials like now, but it's a bit warmer. One thing that you never see in your day after tomorrows and your ice age cartoons and so on is dust storms were a massive thing in the ice age. So this is the American 1930s dust bowl, which was due to drought. Soil dries out, wind whips, you know, this is Tornado Alley, Atlantic territory, and this kind of stuff happened. In an ice age, the glaciers are grinding the rocks into dust, and then spring happens and summer happens, and the glaciers snout the feet proceeds. They've got all this pulverized grit exposed to the higher wind speeds, and it gets picked up and it gets thrown forever because it's really light, small particles. As a result, we have great agriculture all across the North European plain because all that dust got thrown and had to fall out and land somewhere. And there's vast swathes of China. There's rocks called, well, they're not quite rocks yet. Well, there'll be rocks when they grow up, called loess, L-O-E-S-S, which are great for agriculture. When you want to grow cereals and do deep ploughing and things, they're awesome, unless you're a drought. But they're there because ice ages flung that that material acts, and you know, not much chemical weathering, so there's still organic material in it, and it's loose, yeah. So yeah, if you go time traveling to an ice age, you might need to take, you know, your dust mask as well as you know, your parka and your thermal sleeping bag. And I mentioned forests and things, so just to give you a visual here, this is the height of the last glacial maximum at 18,000. Yeah, it's got 22,000, 1,400, but the line in the middle 18,000. The green bits, that's what forests were left in Europe during the Ice Age. I mean, obviously you can't have a forest underneath the actual ice cap, but yeah, the rest of it's gone. And this is what Europe looked like after the ice melted, but before human beings went, oh, farming, chop, 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 set on fire. Right, so that's what the, you know, Europe would look like if human beings hadn't chopped it down and plowed it under. The tree line advanced as the temperature went up, and that from that to that is a global increase of about 5 to 6 degrees. The tree line advanced at 400 meters a year, which is pretty nippy for a tree. That's an average. So some species were a bit laggardy and they advanced 100 meters a year. Oak trees are about bang on the average, 400. And some trees advanced a kilometre a year. Okay? So this is pretty speedy. It also means if we take a standard human generation time as 25 years, 25 years, that's 10 kilometres. So, you know, back in your granddad's day, it was not all trees around here, because they were 30 kilometres away. Those of you that, you know, the kind of quick-witted amongst you will be sort of be going, hang on, all the people that say we can plant trees and stop global warming, back again, you need to plant more than those trees, because that happened while the temperature went up 5 or 6 degrees. There are other things you're going to have to do. You can't just plant the trees, you have to do other stuff to the trees afterwards to get it to take. But these pictures are, this is what kind of ice age climate of an area, and then the trees start to come in and you'll see things becoming extinct or turning into ghosts and things. And then, you know, eventually you end up with, you know, climax woodland there. So the arrival of the trees, lovely and aesthetically pleasing though they are, also has a massive impact on the ecology, and especially on megafauna, big animals. The official definition of megafauna is anything that weighs more than 35 kilograms when it's an adult. So that's kind of Labrador sized, in other words. It's not just all mammoths. You know, podgy Labrador sized.
So a human.
I do love it.
Humans are megafauna. Humans are leopards are megafauna, wolves are megafauna. It doesn't just mean rhinoceroses and you know, kind of brontosauruses and you know, enormous things. Right, so there's this massive impact on megafaunal diversity. So you go from an ecosystem kind of like, you know, Serengeti there, hardly any trees, to one that's more like this American woodland with a mule deer. And the reason is, most of the biomass in this type of ecosystem is animal. They graze down the grass constantly and turn it into animal flesh, and then you get huge mega herds of big things getting eaten by other big things. Whereas in a forest, most of the biomass is this stuff here, timber. And timber is many plant structures are very, very difficult to eat. Eating plants is hard. So congratulations if you're a vegetarian or vegan. Basically, any plant structure, actually any biological structure, so bones and teeth and things, which is about structural strength. So for the tree, bit of wood down there has to be strong enough to support the wood of the entire tree. My ankle bones have to be strong enough to support the, the weight of the entire me and so on. Anything that is physically tough is also chemically tough because it's been built by chemistry. Therefore, it takes a lot of energy to destroy it, I mean digest it. Okay? So, virtually nothing digests wood. And cellulose, the other main structural bit of plants, takes a lot of oomph to do it, and quite a lot of herbivores and things. They're not doing it themselves. They've hired bacteria in their gut to do it for them. So this has got more digestible plants, and it all gets turned into animals. This has got most of the biomass is timber. Right, we'll now go back in time to 56 million years ago. This is greenhouse climate dialed up to 11. This is the Paleocene Eocene thermal maximum. This is the hottest the planet has been since the Cambrian period. There's a kind of map. Obviously, it's 56 million years ago, so continents are slightly different places. India hasn't crashed into Asia yet. Australia is quite close to Antarctica. But you can tell where Britain is on the map. The Amazon basin is a paddling pool. There's huge bits are underwater because sea level has no ice caps. Sea level has gone up hugely. The temperature rises on the map are kind of guesstimates for different bits that scientists have done. But the global average temperature, the estimate went up to 30 degrees. To put that in context, today's global average is 15. Yeah. Sea surface temperatures in the tropics, 36 to up to 40. That is warm bath temperature. It's not too hot to get into, but that's, yeah. So that, this is a picture of all the fossils they found in and around Trafalgar Square from that period. So they're hippos, same species as lives in Africa today. A form of lion, various forms of prehistoric elephants, prehistoric rhinos. It's lasted 200,000 years, and then it dropped back to a balmy global average of 25 Celsius. There were crocodiles in the polar regions and so on. It was caused by, there was a lot of volcanic eruption, putting a lot of CO2 into the atmosphere. And then they think there was a lot of methane burps from the ocean floor, because there was a lot of undecayed stuff down there. I will talk about that in a bit. And they also, as the permafrost melted, you get more methane released, which means the temperature goes up, which means the permafrost melts, which means you get more retaining, which means the ice caps are gone, which means the sea level rises, which means stuff happens on the ocean. But yeah, so it all spiraled out of control. If we get this is what climate scientists who know their science are using as the models for how bad it could get. Okay, so they will be looking at this and talking to oceanographers and paleontologists and so on, and trying to work out what could happen. There are lots of the earth will become uninhabitable for humans. There's a novel by Adrian Tchaikovsky called Saturation Point, which set tropical rainforests in this sort of climate change situation. And humans can't live there anymore because we're mammals and we cool down by sweating. And it's so hot that you can't lose heat by sweating. It's still hot, humid, so you just overheat and die. But you get heat exhaustion and die within 30 minutes if you're not wearing protective gear kind of thing. But you could, go and do tropical agriculture in the Arctic beside the crocodiles. But importantly, again for people that like sci-fi, and the planet did not die. Hippopotamuses, yes, but no, not the hippopotamuses are not dead. However, what did die was everything in the deep oceans. The bottom of the oceans being utterly, utterly dead is a thing in all greenhouse climates, not just the extremes. So this is a diagram of what happens in our modern ocean. So you've got sea level up here at the bottom down there. You get oxygen into it at the top. Waves and wind and so on mix at the top, and oxygen diffuses in and gets out there. That happens in both. So this is saying Jurassic. But the main thing is the pumping mechanism. As sea ice forms, it falls. Dead saline, very oxygen-rich water sinks right to the bottom of the oceans and rumbles along the ocean floors, carrying oxygen to everywhere in the ocean. This pumping mechanism is so strong that water that has sunk in Antarctica and rumbled along the bottom of the Atlantic is still identifiable as coming from Antarctica off the mouth of the Mediterranean. That is a massive conveyor of oxygen and salt around the ocean. Okay, as a result, in modern oceans, we've got lots of oxygen at the top, lots of oxygen at the bottom. The red line is how much oxygen can see into a box. And as things breathe it and decay in it, it drops. But it drops from both things, and there's a zone called the oxygen minimum zone, which is there's a layer in the ocean that is less, the least oxygen. It's a bit, fuzzy boundary kind of thing. Therefore, it's a bit empty of fish and things. Cephalopods appear to be a lot of cephalopods, like the vampire squid, are slightly tolerant to low oxygen conditions. They hide in that. There's pure predators, a shark going, can't breathe. So they hide in that. But a Jurassic ocean, you've still got the stuff at the top. The pumping mechanism, well, you'll get a bit of seasonal stuff. It'll still be dark at the poles in winter for several months, but it's not the huge amount of sea ice falling. You've got that, so the oxygen just down and down and down. And also warm water holds less oxygen than cold water, so you've shifted where it starts from over a bit. So life is only oxygen breathing life is only in the top, and then you've got this low oxygen bit right down, and you've got completely anoxic hot water in lots of places. So like you've maybe heard the bottom of the Black Sea now, it's got lots of bits, there's no oxygen. That's the bottom of pretty much most oceans, and not very deep. So it's the reason places like Wales are filled with grey rocks. Because that grey, the stuff that's making wrong, is undecayed organic matter. It's fallen down, it's in there, it gets turned into rock. So if you see a rock this colour like limestone, there's no organic matter in it. If it's grey, dark grey, coal being the ultimate, black, just a solid organic carbon, that's what it is. So it's great for forming fossils, and it's absolutely rubbish for living in, if you like, oxygen. So everything's going on up here in the shallows. Obviously, a thing like an ichthyosaur, plesiosaur, a dolphin, when they haven't evolved then, is an air breather. It can take a lungful of air and die into this, but a shark can't breathe in this. We're going to our cephalopods with my study cephalopods here. So I said that the cephalopods have the low oxygen tolerance. Nautilus, they've done tests on. These things are very like apparently Nautilus, except they are much more complicated in their internal structure in their shell. It's not just simple chambers. The shell is full of little chambers of pockets of air. And that's probably a maximising surface area, so they can pump liquid and gas in and out really, really quickly, like a submarine flooding its ballast tanks. And scientists speculated that basically these things go, oh, shark! And crash dive into the oxygen that's meant to escape. So they would be able to dodge a lot of any fish predators, squid, things that are water breathers, they can dodge. But something like an ichthyosaur would be able to follow them, but an ichthyosaur will suffer from the bends if it goes too deep. So if these guys can survive crash diving, below the oxygen bit and then into where the ichthyosaur can get the bends, they're safe. Oh, and there are little pockets of gas. contain some oxygen, so they've got their own little scuba tanks. Okay, so we will go a bit further back in time. I mentioned that greenhouse, it's normally wet, but if you get a supercontinent, you can get super deserts. So this is what the supercontinent Pangaea looked like. So all our modern continents marked on it have ran together into one gigantic continent, and here are some of the inhabitants of Pangaea. What this worked is normally winds are picking up moisture as they cross the ocean, they reach the land, and clouds form, rainfall all the time. But you can get a rain shadow effect where you get deserts now because there's not enough. Either clouds rarely get there or don't get there. So there's areas where there's no rainfall. This is so huge. There are vast swathes of the continent where this rainfall never happens. If it's in the tropics, it's a hot desert like now. If it's at the poles, it's a cold desert, like you've got the dry Antarctic valleys now. They probably also had them in mid-latitude, so you would have somewhere that has the rain, the climate in terms of temperature of Plymouth, but no rainfall, and you get something that we don't have now, which is a mid-latitude desert. But all that rain still has to fall somewhere, and there's a lot more of it when you've got a greenhouse climate. So in the Triassic, they had what was called mega monsoons. It's falling around coastal areas and places. So it's like the Indian monsoon, it's seasonal. They would have dry winters and rainy summers, and by rainy summers it makes the, they call it a mega monsoon because the amount of water they calculated was falling. It makes the Indian monsoon look like a brief drizzle. It would just rain constantly for months. And then you've got the deserts in the middle and so on, which are going to be roasting by day in the tropics and freezing by night because there's no cloud cover, so there's no heat trapped, it all just evaporates away. And I'll give you an example of how your time travellers might have unexpected consequences for that kind of thing. Neil Nightingale, who was head of the Natural History Unit, BBC Natural History Unit, they went out to film a series about Australia, and they were filming in the central Australian desert. And Neil came back and he said, well, he was expecting it to be really hot during the day, and he was expecting it to be really cold at night. What he wasn't expecting was the first thing he had to do every morning when he got up and climbed out of his sleeping bag, lovely thermally insulated sleeping bag, was beat the ice off it. Because he's in a little tent, breathing, because he's a mammal, and all the moisture in his breath has formed a layer of ice over his sleeping bag during the night. So, yeah, that's the first thing your time travelers will have to do every morning is clean the ice off their sleeping bags. Now, it's not just the past. Your time travellers may have encountered supercontinents in the future. So there's Pangaea again, that's today. But we know what direction the continents are drifting in and what they're likely to collide with. So there's some modelling being done of different supercontinents that will form at different times of the day. We've been given them Novo Pangaea, Amasia, and Pangaea Proxima, different kind of estimates of what the continents will be up to in 250 million years. Though, of course, we know from Doctor Who that the National Trust moves them all back again. As Christopher Eccleston's doctor said, that is a classic Earth. I can't help wondering if someone noticed the special effects people had, not the confidence and quickly thought of an excuse. Right, so we shall jump further back in time to Carboniferous, where there's an oxygen high. So fire has always been a hazard back in the past. We've got here's the Silurian, and then later we've got dinosaurs. So lightning strikes, volcanic eruptions, careless time travellers with matches. You know, in the Carboniferous, however, it was a major problem because the oxygen back then was 35%. Yeah, so I think I'm going to do, yeah, skip on too. So, you've doubtless had fire safety talks at work about the fire triangle, that you know, oxygen, fuel and heat. If you jack that up to lots, you don't need nearly as much of this to get that to ignite. Yeah, so 35% is significant. It's 21% now for those that don't know it's significant. Oh, it's 21% now, except our oxygen is dropping as the carbon dioxide goes up. So it may not stay. It's we've actually lost a bit more oxygen as well as gained a lot of carbon dioxide because an atom of carbon plus a molecule of oxygen equals a molecule of carbon dioxide. So you remove one oxygen molecule to make one carbon dioxide molecule.
What level of oxygen?
There are scientific papers speculating about what happened to people that live at altitude like the high Andes and Tibet and so on if the oxygen drops significantly. I mean, it's
35%.
also 35%, you're probably going to run an oxygen high, and it's combined with different levels of carbon dioxide. So our physiology, the oxygen would go, yeah, you don't need to take breaths as often. And the carbon dioxide detectors would go, you need to go, and yeah, it would cause, I don't think anyone knows what you would do. You might develop breathing arrhythmias, or you might just acclimatise to it the way that you do. But anyway, this graph, the red and the blue are different scientific models of what the oxygen was like at any given point in time, but they both agree it was really high in the kind of Carboniferous to Permian transition. This is where forests evolved. Back here, 400 million years with that dotted line here, that's when plants first came out onto land. Okay? And this dotted line here, which starts not long after, is when charcoal starts turning up in the fossil record. So basically, plants moved onto land, went, oh, isn't it lovely? Boom! And they pretty much things started catching fire pretty much as soon as we were out of land. And how much fire is part of the ecology can be measured when we find charcoal, and it use up a lot when there's all these all this hugely high oxygen. That's the time you've seen things about giant dragonflies and giant this, that, and things which they're saying, oh yeah, maybe the insects and arthropods can do that when there's lots of oxygen. And you can end up in a feedback loop, because if stuff catches fire, you will produce charcoal as a side effect, which will end up buried in the soil, taken out of the atmosphere, or it gets blown out to sea, and it causes productivity here, which costs more oxygen, and sinks and gets removed from the soil, which means more oxygen, which means you're more likely to have a fire, which means more charcoal, which means more oxygen, which means you can end up in a feedback loop. Yeah, positive feedback loop. And because charcoal doesn't rot, I mean, timber is difficult to digest, and only kind of bacteria and some fungi do it. Charcoal is just, but you can solve global warming by going to your local DIY centre, buying charcoal briquettes, and then finding a salt mine to bury them in so that they, remove carbon from the atmosphere. And you'll know if that and the tree planting and so on works, because our oxygen will start going back up again. So the oxygen that we've lost, which is only 0.7% in the last 100 years. I've seen estimates of like from 0.1% to 0.7%, because I don't think many people are measuring the oxygen and also arguing about where it was to start with, and what altitude you're doing your measuring at. Right. So further back still, we're going to the Devonian, when animal life has come out onto land, and there's giant amphibians and things. So, the Scuffley Creek colonies moved onto land 419 million years ago. Plants were out long before them. Plants started getting woody stems and protective. They are racing for the light. They need to be tall. They need to have structures to get them up. They can't just sprawl around like seaweed at low tide anymore. So they're developing woody stems to do this race for the sky thing 400 million years ago. Vertebrates, our ancestors, another 25 million years later. But vertebrates only evolved the ability to be plant eaters, herbivores, at the beginning of the Permian. So it took 76 billion years for vertebrates to work out how to eat plants. Even fungi didn't work out how to eat wood. Fungi being the main method of decaying wood these days. Until 290 million years ago. Eating plants is hard.
What did they eat before they eat wood?
Aha! So, this is what we're used to as a modern food chain on an Earth-like planet. We've got plant, herbivore, carnivore. You've seen a million wildlife documentaries, so it's pretty much this. It might be plant, caterpillar, blue tits, sparrowhawk, but it's a short food chain and it's not very easy. The original terrestrial food chain was like this. Plant. The plant then goes and dies, unassisted by any animal, and it rots. Bacteria are getting at it, but nothing else. Fungi haven't figured out how to do it yet. Things that are eat rotting plants, so they are maybe mostly working the bacteria, but they're getting some of the nutrition from the rotting. The bacteria are doing the heavy lifting, and then something eats them, and then something eats them, and then something eats them. There were huge long food chains of carnivore, but it gets just getting bigger and bigger and bigger. I mean, there weren't very many of these because there's energy loss at each step. But it was to misquote Terry Pratchett, carnivores all the way down. So some of the old Hollywood movies where time travelers and find lost worlds and things, where everything is trying to eat them, may not be an exaggeration. Okay, so if you go back to the Devonian or whatever, any giant amphibian, and it's not a herbivore, it'll want to eat your face. Giant spiders want to eat your face. Giant dragonflies want to eat your face. And then we can skip back. We're still in the Devonian, but also earlier, from the late South Island into late Devonian. It wasn't. I said fungi didn't get around to learning how to eat plants till quite late on, but they were there, and they were a bit bonkers. So this structure here in the rock, geologist for scale, is a thing called Prototaxites. It was a giant fungus, some kind of giant mushroom thing. So 3 different artists and collections of what they looked like. They got to 8 meters tall and 1 meter in diameter. They may have been able to photosynthesize, which modern fungi can't, or they may just have had a fungal lifestyle. But they were absolutely bloody huge. And animals were burrowing into them and using them as things to live in. They didn't seem to be eating them very much because they were all eating each other. So we had this weird ecology that we've never seen anything like it or since. So lots of photo opportunities for your time travel. Yes, lots of mushrooms at the corn breakfasts. Before plants and fungi and the animals, I think it's actually one of those Eurypterid fossil sea scorpion things. That's the technical term, sea scorpion. Right, before the plants, the fungi and all the rest of it, the only thing you had on land is where places where rocks would get wet, you know, it's Bristol, it's Plymouth, it rains a lot, and you would get bacterial slicks and algal slicks on it. This is a low tide thing, but imagine this, but it's somewhere where it rains as opposed to tide comes in and out, and then you know, kind of slimy sort of thing on a rock. This is all you find. More of it around the edges of lakes and rivers, but inland as well, because you know spores can get blown inland and so on. So a bit dull, bare rock, slimy stuff, you know, coating the rock.
And when you flip the card over, it says "Welcome to Morecambe."
The oxygen at this point in time is about 10 to 15%, so not very good. The carbon dioxide is between 11 to 18 times the pleasant level, which, you know, so you were getting altitude sickness symptoms from the low oxygen, but you will also be getting headaches and dizziness and so on from the high carbon dioxide. Health and safety in the workforce says a carbon dioxide level of 13 times our atmosphere in a workplace situation, maximum of 8-hour limit you're allowed to stay there. So if you went back there, your time travelers either have to have a maximum of 8-hour stay, or you're going to have to take breathing equipment. I mean, you know, you need supplementary oxygen anyway. But the whole place is empty apart from that slick of bacteria and algae over rocks. So you'll have the bits where there's not much rainfall and everything is empty, but you'll also have, when these unfortunate people have crashed their spaceship, bits where it's utterly empty, barren rock. And it rains all the time. The upside is, if you find a planet like this, is you've got a leg up on terraforming, you've got the 10 to 15% oxygen already, so, you know, and you're not fighting local ecosystems for space and so on. The downside is, if you're a nasty colonialist and you want to go and conquer people, unless you really like shouting at rocks, you know, you've got no one to fight. So the seas at this time of time are teeming with life. Okay, so you know you can go and shout at Ammonites, yeah, and you can the ancestors of the Ammonites. So the seas are teeming with life. So you can go off and you know launch your fishing fleet and come back with lots of delicious things to eat into calamari and fish fingers. But on land, there's only you. So you've got you know you can go somewhere. You could go somewhere, you know, an inland basin where what you're doing with agriculture is not going to leak into rivers and head out to sea and wreck the ecosystem that's already there. If you pick your spot, but it would have to be somewhere like, you know, the Danakil Depression or Death Valley or somewhere where everything is pointing in rather than will eventually flow down the Amazon and reach the sea kind of thing. Back a bit further, between 717 636 million years ago, known as in the Precambrian, known as the Cryogenian period, because it was bloody cold. So this is controversial, because the snowball Earth theory is based on the fact they've got rocks which they think were at the equator and show evidence of glaciation. However, when you're this far back, you're not quite, you're where you know the old continents were is a bit of guesswork. So what some folks say, no, it was right on the equator, might have been, you know, up at the Tropic of Cancer or something instead. So it's controversial. It was a global glaciation. It lasted a long time. So it couldn't be quite like Snowpiercer, because life survived, and life is only in the oceans at this point in time. So there must have been ice-free bits, so that enough sunlight gets in photosynthesis to sustain an animal ecology. You know, there were animal life forms there. EDI county.
I'm being a bit dumb here, I should know the answer. But when did we appear? Millions and millions of years
Oh,
ago.
we're in. Remember, I was talking about a series of ice ages
Yeah.
right at the start. Modern humans are only about 300,000 years old. Our Homo, our genus, and sort of like our ancestors, the Australopithecines, are about 5 million years old, 3 to 5 million years old, depending which species of Australopithecine you come from.
We arrived an hour ago.
Yeah, we're the 2 minutes to midnight on the 24-hour clock of thing. Yes, so there must have been ice-free areas round the poles, and also possibly, like we get in the polar regions, things called polynyas, where, despite the fact it's freezing cold, there are bits that don't freeze for reasons. And anywhere there was hydrothermal vents or volcanism would have temporary melting as well. Right, so that's us right back to snowball Earth in the Precambrian. So I shall just to summarise. Health and safety for time travellers. So beware of dust storms if you go into the Ice Age. You will need air conditioning in your hotel if you go to the Paleocene, Eocene thermal maximum. Deep sea fishing in the Jurassic is pointless. Don't play with matches in the garden. Everything will try and eat you in the Devonian. People with mushroom allergies. that time period. There is nothing to conquer or talk to in the pre-Silurian. Wrap up warm for snowball Earth. And PPE and bathing equipment aren't just for alien worlds. Any questions? Oh, yeah.
You talked quite a bit about the movement of the continents. Is that dependent on Earth temperature? Does that accelerate or decelerate the movement of the plates?
No, there's stuff going on in the mantle. So there's currents in the mantle. The way if you put a pot on the boil, you get convection currents. Much like in the atmosphere, you get convection currents and things. And water is part of it. In the water in the minerals, not like water sloshing around in a bucket, is part of the lubrication. So whether the magmas and things are hydrolyzed or not, basically if you run out of water like on June, continental drift will stop because it's sort of lubricant, but it's a lubricant in a funny way. It's not like there's water between two continental plates, like there's skating on it, like aquaplaning on it. It's like the composition of the magmas and things. But yeah, there's deep mantle plumes and there's convection currents that are pushing things apart and so on. So yeah, cool, 10 minutes. So the fact that it's freezing cold or tropical everywhere outside isn't really going to affect that much. I think the only thing you'd say is that when you've got an ice age, the mass of the ice does depress. Like Britain is Scotland was shut down during the ice age, and England was kind of sticking up a bit, sort of thing. And as the ice melted, we're tilting the other way. So Scotland is rising, and England is slowly sinking. But it's minuscule, kind of.
He's the Scots.
Yeah, I think good job I just sold my house in Bryson then.
Any other questions?
On your rising one, there's the famous rock in Sweden, which was marked by a geologist just in the pre-Victorian period. And of course, his mark is now nearly a metre above the current sea level.
There's a harbour near Vesuvius. It's not Herculaneum, kind of thing. There's some other where the fishermen used to come in as a fishing boat and step off onto the dock, and now they come in and climb up a ladder onto the dock because Vesuvius is slowly rising. and the landslip, which means Vesuvius is going to be erupting it. They're getting better at predicting it, but they're not getting better at planning for what will happen if it does.
Yeah, sorry, ready personal comment or question, but on the other point about is high oxygen toxic, I could be wrong, but were the Apollo 1 astronauts not in a pure oxygen atmosphere that was at sea level pressure? And that was a problem, that's why it burned so bad. And then after that they changed Apollo so they'd start off in a conventional atmosphere where they launched, and then during the ascent they would purge, because in orbit they were in a pure oxygen atmosphere but at a much lower pressure.
Yeah.
So the amount of oxygen was the same, which is why when they dumped on the soil they needed an air.
Yeah.
But in the Apollo 1 test, they had the really bad combination, I think, of sea level pressure,
And too much oxygen.
but pure oxygen.
Yeah, I
And
don't
so
know
everything,
about
that's
that.
why everything in the capsule burns.
Yeah. Yeah, I mean yeah, there's also, the scuba diving mixes, you've got all sorts of things in there to cope with. But pressure I haven't mentioned because atmospheric pressure hasn't changed much over this kind of time period, but obviously alien worlds, atmospheric pressure is going to have a problem there as well. So you were first.
Is there really anything we can do, or is the planet going to carry on its merry way?
You mean global warming?
Yeah.
Climate change. It's basically kind of governments and corporations and you could do stuff, but first of all they've got to stop. We sent all our oil executives to Australia, but we planted 3 trees. It's just greenwashing, and I don't think enough actual climate scientists have talked to freaking geologists and archaeologists. They're just talking to zoologists, some of whom don't know this stuff because they don't care about mammoths. But things like there was a lady on a thing on Radio 4 the other day, who was a recycling expert, and they were talking about paper recycling, and she said, "Oh, of course you can't recycle shredded paper," and the audience went, "Oh!" No, the fibres aren't long enough.
No.
You can have a,
Every time
And then later she said, "You cut someone said, why are yogurt pots not recyclable?" And she was going, "Well, they're basically too small. By the time you've broken them down again, you don't have enough stuff to make something new." And I'm still going, but you collect all the shredded paper, and you collect all the yogurt pots, and you collect all the Dan Brown novels that the charity shops can't sell because there's thousands of them, kind of thing, and you put them down a salt mine, and you have removed tons of carbon from the atmosphere. The planting trees, it's great, but it's temporary, and trees breathe, so it's not. What you need to do is chop the trees down, turn them into charcoal, bury them in a deep ocean trench or down a sand. So there's lots of stuff we could probably do with carbon capture. This is not expensive technological things about, oh yes, I shall turn it into carbon dioxide, blah, blah, blah. But tech bros don't want, if they want a tech solution, they don't want lots of people posting their yogurt pots to Cheshire and some bloke with a wheelbarrow trundling them into a salt mine and pulling them down a hole,
So are you saying we should go back to landfill?
Not landfill, because you have to take it away from,
Okay.
it has to be away from oxygen and away from water, so salt mines are ideal.
Yeah.
But some abandoned coal mine, that if you package it in something that's waterproof, and so if water gets into the mine.
You're saying put the coal back at the coal mine?
Yes, but I'm basically saying that the problem is we have turned rocks into atmosphere. Turning atmosphere into trees is not a solution. You have to turn the trees back into rocks by basically removing them from the biosphere. 5 minutes, yeah. So any you had a question? Sorry, I'm ignoring this part of the audience.
We don't feel slighted.
You had an ice cap on June.
Yes. Frank Herbert had an ice cap. He drew the map.
Frank Herbert lied had an ice cap
Yeah.
on June. I assume you wouldn't have an ice cap if there was less water in the night maybe that fashion.
You would probably have an ice cap covered in dust in June, therefore it wouldn't evaporate. But also, it can be freezing cold in pools, therefore the ice is not.
I suppose what I'm saying is, all of this, the history of the Earth,
Oh, yeah, yeah,
the mix of the elements of the Earth,
yeah.
and different planets might have different mix of elements, and therefore it would be different in the way it happens.
I don't know what your question is then. If it's made of launch, your planet, yes, that's what you mean by different mix. I mean, you could.
Yeah, well, I realise I've just done a statement rather than a question.
Yeah, if it's formed the way Earth formed, there will be oceans, but you could say that, you know, how much water there was for outgassing from the rocks and how many comets hit it. You might have more continent and less ocean, but that you will have continents. And I mean, continents start out teeny and then they grow and they grow. Because I've just been talking about life. You know, you basically start out with water, but the seas are really shallow, and then you grow to continent, and then it gets eroded away. You grow bigger, and they accrete, and they get bigger and bigger, and then until you get, you know, proper grown-up continents like we have. I've got a question at the back.
Yeah, okay, I'm actually not following people to be. How about chucking bodies down in salt mines? Does that help?
As long as they don't decay.
Have you got any bodies in mind?
You can open them up and pack them full of salt.
Salt, yes. It's you want the organic carbon. The carbon actually it doesn't even have to be organic carbon because yogurt pots. It has to be put somewhere where oxygen can't get it at it, so it can't decay and turn into more carbon dioxide. So a tree is, you know, grabbing carbon dioxide, growing the timber, and then the tree dies and it rots and it all goes back. Or some bugger sets it on fire and it all goes back. But if you set it on fire without oxygen, so it turns into charcoal, you know, proper charcoal making, you can then bury the charcoal briquettes and you've taken the carbon out of the system. And so on. So it's a simple, you know, it's a.
No, I'm actually going to ask you a question.
Oh, okay, but I thought that was a stop now.
No, not yet. My question was, in that case, the Egyptians actually had the right idea.
What, to mummify?
Mummify everything.
Yes,
and is it they have the wonderful like salt that they got there? They just put the body and let it. Natron.
Yeah,
That's it.
Yeah. Yes, but they had the foolish thing that they, you know, hid treasure with their mummified bodies. Now, people kept breaking into the tombs and exposing them to oxygen and all the rest. Oh, and the Victorians found huge, you know, all the sacred animals, the mummified cats and the mummified ibises and things. They imported them to Britain and ground them up for fertilizer.
Also, we exported steam engines that could take them as fuel.
Yeah. Any more questions? We've probably time for one more question. Sorry, Dave. Yeah. One more. Anyone?
What time is it?
10 o'clock.
I've spotted the time traveller in the audience.
Please give a thunderous round of applause.